Section 11.9, Bernoulli's equation. Before we dive into what that equation is, let's take a look at this conceptual example. Tarpaulins, or tarps, and Bernoulli's equation. When the truck is stationary, the tarp lies flat, but it bulges outward when the truck is speeding down the highway. Account for this behavior. What is going on here? You may have also seen this if you've ever seen someone drive a mattress strapped to the top of their car. You can see the mattress lies flat when they're in the parking lot, but then they hit the highway and that mattress is flying upward. That's why often mattresses end up on the side of the road. So be cautious. What is going on here? Why, when you start moving, would it go up? Seems very odd. To help us understand it, we need to get at the ideas that are in Bernoulli's equation. So we're going to come back to this. Let's first go back to our fluid in a tube. We saw when it was wider, the fluid was moving slower, and when it got narrower, the fluid was moving faster. That means when the cross-sectional area was changing, the fluid had to accelerate. It had to increase its speed from the constant speed in the wide section to the constant speed in the narrow section. There was that brief acceleration. If we put a pressure monitor there, we'd also notice that when it's moving faster, it's at a lower pressure. And when it's moving slower, there's actually a higher pressure there. So the fluid is accelerating toward the lower pressure regions. Okay, that's a good note. Another note is according to our pressure-depth relationship, then the lower you are, the higher your pressure. This is assuming that the area of the pipe doesn't change, because the area of the pipe is what sets how fast the velocity is moving. So if the area of the pipe stays constant, then the velocity has to stay constant, but the pressure will then change, and we'll have a higher pressure at a greater depth and a lower pressure as we move upward. So how do we pull these things together? Well, Bernoulli's equation relates the depth, the speed, and the pressure of the fluid. So it's a very powerful equation. There's the details of the derivation here, and there's even more in the textbook. I'm really going to skim over them because you don't need to know the derivation. You mostly need to understand the end result. But the key big idea is that it comes from the idea of work and energy, and our end result will actually be a restatement of the conservation of energy for fluids. So that's pretty nifty. So we're going to be comparing two different points here, right? Point 2 that is at a height of y2 and is moving with some speed v2 and has some pressure p2. And that will be compared with point 1 that has its own speed, pressure, and height y. And so you could calculate the work done and relate that work to the change in pressure times the volume, but we also know the work is equal to the change in mechanical energy, the work done by non-conservative force. Turns out the work done by the difference in pressure is a non-conservative force. So we have this conservation of energy that pops up in here, where ultimately we can show that the difference in pressure, P2 minus P1, is equal to the quantities of 0.1 minus the quantities of 0.2. So if we rearrange things so everything becomes positive, we arrive at what's known as Bernoulli's equation. So in a steady flow of a non-viscous, incompressible fluid, the pressure, fluid speed, and elevation at 2 points are related by this equation. And this is a really useful equation. It's like our pressure depth equation, but even better because it doesn't have to be static anymore. So we have pressure at point 1 plus 1/2 the density of the fluid times the speed at point 1 squared plus the density of the fluid times g times the elevation at point 1 is equal to all of those same quantities at point 2. The pressure at point 2 plus 1/2 the density of the fluid times the speed at point 2 squared plus the density of the fluid times g, 9.8, times the elevation at point 2. It's a lot packed into it, right? But we can notice a couple of things. One, this 1/2 rho v squared, that looks a bit like our kinetic energy, right? We previously saw that kinetic energy is 1/2 mv squared. This is much the same idea. It turns out this is actually the kinetic energy density. Sorry, I should make this a KE. To make it a little clearer. So kinetic energy is equal to 1/2 mv squared. Now instead of mass, we have the density. This is an important note. The density rho is not the same as the pressure P. So I try and make the pressure a really large capital P and the density a curvy lowercase p. These are not the same. I too often will see students in the heat of the moment on a test say, oh look, I can just divide by P or divide by rho and everything cancels out. If the pressures are not the same, you can't divide the density out. So you want to keep that in there. All right, the rho g y also looks a bit familiar. That's like our potential energy, right? So we saw potential energy is equal to mgh, or you could write as mgy if you wanted. So instead of mass, we have density, which is mass per volume, times g times the height, the elevation. So hopefully that starts to give you some sense of this, right? And this equation does simplify if two things are the same, right? If y1 is equal to y2, we don't have to worry about anything with the y's. Those two terms will cancel. So let's look at a couple of applications of Bernoulli's equation in action. So one is airplane gliders, right? So airplanes that have carefully designed wings that are actually larger on top. I always thought it was the opposite. I thought for sure it would have to kind of bulge outward, and that way the passing air would sort of push it upward and blow it up. But it turns out it's actually a longer path on the top. There's an intentional planning here. That's because the air, as it passes around the wing, it wants to stay together in steady flow, right? If you make the wing too different, then it's just going to break up and be turbulent. But if you can keep that steady flow, then the air is going to try and stick together. That means if on top it has a greater path to travel, it's actually going to travel faster to catch up with the air that's traveling down below. So the air above will speed up compared with the air below. The heights here are about the same. So we could look at the case that y1 is about equal to y2. And in that case, these two terms go away. And all that we have is the pressure and the velocity. And the velocity is already set. So really Bernoulli's equation tells us a lot about the pressure. So if the velocity goes up, if it is going faster above, then that means to keep the relationship constant, the pressure is going to have to drop. It's a lower pressure above. Similarly, if the velocity is slower compared to above, if that's a lower value, then the pressure is going to then have to be higher to keep everything balanced. But if there's a difference in pressure, that's enough to then create a net force, right? Because we know that pressure is equal to force divided by area. So we can look at the difference in pressure, and that'll be equal to the difference in force relative to the area between them. And it will be pointed net towards the lower pressure. So that means we're going to create an upward force known as our lift force. So by just having a slightly asymmetric wing, by Bernoulli's equation, we can create a lower pressure region and thus create lift, an actual force. Amazing. Now that we've seen this, let's go back to our truck example with the tarp on top. Why, when it's driving on the highway, does the tarp bulge upward? Well, if we think about it, when it's stationary, the air is at the same speed in either case, right? V is equal to 0 above, and V is equal to 0 below. That means that the pressure will be the same in both cases. So P, say 1, and P2 are just going to be the same. So all is balanced and good. But when you start driving down the highway, now there's a whole bunch of air moving very quickly above the top. If you have a region with fast moving air, what's that going to do to the pressure? That means up here, the pressure is going to drop because the velocity is so much higher. Down below, the velocity of the air, the fluid, is still 0. So we have a larger pressure down below. If we have a larger pressure down below, guess what? The tarp is going to go to the area of lower pressure. It's going to bulge upward and move towards the fast moving air. So there we have our explanation. So next time you see a truck going down the highway with a tarp over the top, you can know that's just physics. A couple more examples of this because it's just really cool. If you've ever looked under a sink, there's a U-shaped tube that's known as the P-trap. And that's there so that you don't smell anything else from the sewer that your sink is connected to, right? Because your sink is connected ultimately to the sewer. There's some stinky things there. So if you keep water between you and the sewer, then all is well and good. Well, houses with that U-shaped P-trap, they connect it to a vent to the outside before sending it to the sewer. Why is that? Is it just to ventilate the sewer so it doesn't get as stinky? No, there's also a really good physics reason. And that's because other times, like when you use the washing machine, you get a whole bunch of fluid coming out of the washer, moving very fast along the main tube to the sewer. Well, guess what? If you create fast moving fluid, that's going to drop the pressure at another point, like at the connecting point on the water-filled trap. The pressure drops there, but it doesn't drop in your house. Pressure in the house is still 1 atmosphere. Then the pressure in your house is going to push this water to go to that lower pressure region. You will lose all the water in your P-trap and you will smell it. If instead we add this vent to the outside, then even when we get the high velocity water coming by, it doesn't drop the pressure in the trap because there's this vent to the outside that keeps you connected to the 1 atmosphere, which is the same as what you have in your house. Whew. So you get to keep the water in your P-trap and there is much rejoicing. All right, one more example is a curveball in baseball. That's also the same idea. So if you throw a baseball straight to the baseball, it looks like the air is passing around it on both sides, and the air will have to bend to go around it, and it will bend equal amounts above and below. Okay, so that's all fair and good. This is a top-down view, by the way. Now, if you throw the ball with spin, so that the ball is spinning as it moves through the air, then you create a really interesting effect. Because at some points, the baseball is moving against the natural flow of the air, and so it actually slows the air down. At other points, it's moving in the same direction as the air, and so it helps speed the air up, so you get faster air on the other side of it. If you have a region that's faster air versus a region with slower air, you're going to get a difference in pressure, right? There's going to be a difference in pressure, and there's going to be a force on the ball toward the lower pressure region, toward the area where the air is moving faster. So that creates the sideways force on the ball from it spinning so that it no longer travels in a straight line, but it whoop, bends off to the side. And this, once again, just comes from Bernoulli's equation. This is another example where the y's are constant, it's the same height, but based upon the relative speeds, you get a change in pressure. And that's what Bernoulli's equation will tell you. It tells you about the pressure at different points. If you have a difference in pressure, there's going to be a net force, and then you can see some really cool effects.